Okay, so good afternoon, everyone. Welcome to the N3AS room seminar. We are glad to have Soumya Bhattacharya to be our guest speaker. Soumya is now the final year graduate student at the Tata Institute of Fundamental Research in India, and he will join the academia syndicate in Taiwan as a postdoc in this fall. He will talk about the theory of fast flower conversion of supernova neutrinos today. Soumya, please take it away.
Okay, sure. Okay. Uh, so is my screen visible? I mean,
Yes, I can see your screen.
okay, thank you. Okay, thanks for the invitation. I will be talking about theory of fast flavor conversion of supernova neutrinos based on my recent works. So the title of the talk is basically like this. So I will give some background and typically the challenges in this field, and then talk about the works that I have done typically in three parts mainly. First, I will discuss the numerical recipe that we have developed, and then the typical theoretical development we did in this field. And lastly, I will talk about how did we extend our calculation towards multidimensional system, and end with the conclusion and phenomenological consequences. So to give a brief overview, typically like supernova, we will be talking about stars which are like 8 to 10 solar masses, which at the end of their lifetime actually mostly becomes a iron core, and then due to gravitational and it accretes matter on it, and this is which is known as the implosion scenario. And when it accretes matter on it, like when it becomes reaches the Chandrasekhar limit, it basically becomes stiff, and then there is a it bounces and creates a shock wave, and and during this time it emits a large number of neutrinos, and then the star explodes, and these neutrinos, like to get the information about the star's astrophysics, these neutrinos play a important role, and typically it's important to know how the flavor conversion happens for these neutrinos that are emitted, because that can have a big effect on the nucleosynthesis and also the astrophysics related to the star. So we will be talking about mainly the typical, like in this talk we will be focusing on how the flavor conversion happens with these neutrinos which are emitted during this explosion. Typically this type of in this type of scenario, the neutrino density is very high, and the equation of motion basically deals with, it's better to understand the equation of motion in terms of the ensemble or this density matrix formalism, where basically the diagonal elements of this density matrix basically captures the total flavor content of the neutrinos that are emitted, and the off diagonal components captures the amount of flavor conversion. So typically in this dense scenario, the equation of motion which governs the neutrino flavor conversion is basically given by this type of equation, which is basically where the Hamiltonian has basically three parts in it. The vacuum part comes from the usual vacuum oscillation that is seen. The matter part is basically due to the density profile that is there inside the matter profile that is inside the supernova, and when neutrinos interact with the background matter, it creates a matter potential, which is basically responsible for this MSW type of resonances. And there is this extra piece of term which comes in this type of special environments, which is due to the neutrino-neutrino interaction term. And this neutrino-neutrino self-interaction term basically causes something known as collective effects or fast conversion, which we will be going to mainly focus on this talk. And this one can see this self-interaction term has a coupling, and also it's non-linear. Due to this term, it's the equation of motion is non-linear, so which makes the problem quite challenging and non-trivial. So this coupling due to this integral and also this extra rho inside the H self makes the system a non-linear equation of motion. So typically due to this typically Hamiltonian, this the neutrino oscillations that is mainly seen in this environment basically has typically different parts in it. Firstly, when the neutrinos are emitted from the core, there is no oscillation, it's basically trapped. After that, when it moves around roughly at the 10-kilometer level, when the self-interaction term is very high compared to the vacuum and matter term, basically there is something known as fast collective of conversion that happens. Then after some time, around 100 kilometer, there is something known as slow collective conversion happens when the self interaction term is of the same order of the vacuum term or the matter potential. And after that, there is only the self interaction term, the neutrino density basically falls a lot, and then self interaction terms is basically negligible, and only the vacuum and matter term dominates. And then the usual MSW conversion happens. And when the neutrinos are emitted outside the star, typically in the interstellar space, basically there is only vacuum term which governs the flavor conversion. So we will be interested in this talk in this regime around R10, which is like around 10 kilometer from the core, where basically the self interaction term is very high and fast collective conversion occurs. So this is the region which is our main focus in this talk. Okay, to give a review of what is fast flavor conversion, typically these are flavor conversion of neutrinos which happens very close to the supernova core, around few kilometers. It happens at a rate which is typically proportional to the neutrino number density, the amount of neutrino that is present in the core, and the rate is typically very fast compared to the usual neutrino oscillation that we see in vacuum or ordinary matter. And also, so this plot basically explains how this flavor conversion happens. One can see that with respect to time, there is an exponential growth in the flavor. So and it's quite fast. And this left plot actually explains one thing. So this flavor conversion requires a zero crossing in the neutrino angular distribution, and basically it's independent of energy or mass hierarchy. So this is one important point that is important for fast flavor conversion to happen. Basically, the neutrino angular distribution has to go through a zero crossing. So typically, in this framework that we developed, we will basically sticking towards two flavor framework, where we consider only neutrinos of two flavor. And in this scenario, one can write this density matrix in terms of a polarization vector language, basically one can expand this density matrix in terms of the Pauli matrices and the identity matrix, and this helps us to write this density matrix into equation into a polarization vector language, where basically the parallel component of this the third component of this polarization vector captures the amount of flavor conversion, and the first two components amount, like the third component captures the amount the survival probability, and the first two components represent the amount of flavor conversion of the system. And the equation of motion becomes like this. So sticking to this equation of motion, we will be basically, as we are considering fast conversion, we will be neglecting the vacuum and matter term and only consider the self interaction term, which enables us to write this equation of motion in this form, where basically the GV captures the angular distribution of neutrinos, and as I said, the parallel component of S basically amount of flavor content, and the perpendicular component represents the flavor conversion. So this is our basically equation of motion that we will be dealing with. So to give a hint of what are the difficulties and challenges in the field, basically this equation of motion, as we can see, is a 3 plus 3 plus 1, which is a 7-dimensional problem, which is a huge phase space dimensionality. And what we try to do is to partially resolve this problem using a multi-dimensional framework, which is much more close to the realistic profile. The next thing is that the equation of motion is very it's a large number of equation of motion, partial differential equations which are coupled and typically non-linear. So we try to develop an analytical techniques and numerical code which can resolve this problem. There is another difficulty, is that there are lack of numerical techniques which can give accurate and precise result in the nonlinear regime. So we developed our own code which gives accurate and precise answer even in the nonlinear regime. So there is another point is that there is a lack of theoretical development in the nonlinear regime. People pretty much developed a theory in the linear regime using linear stability analysis. So we tried to develop our own theory which can predict how, when, and what extent flavor conversion happen typically in the nonlinear regime. So to firstly introduce our numerical recipe that we will be using to solve this equation of motion. So we used a code like typically which has this which follows this numerical strategy, where we first discretize our spatial direction into two components. Like we discretize the spatial directions into the different spatial beams for each velocity mode. Then we as a result we get a set of coupled nonlinear partial ordinary differential equations instead of partial differential equations, which basically is, makes the system a bit much more simple. To use in this method we used our method called fast Fourier for transform, and also use periodic boundary conditions over space to basically discretize these equations, and also we use this scipy.fft solver to discretize, and then we solve this set of ODEs in time using our zboard solver in Python, using a backward differentiation method, which basically solves the equations of motion in a very fast way compared to other numerical techniques. So typically we use this we use an angular distribution which is like a box type of spectra with a zero crossing around the v equals to 0 mode. This type of angle for this angular distribution we in this talk we mainly focus for the phase dimensionality, which is like one time and one space and one momentum mode. We use an initial condition where neutrinos are emitted as purely electron flavor states. We give with a small perturbation in the off diagonal element. So the solution for the equation of motion basically looks like this, where the neutrinos start with purely electron flavor, and after some time it converts to the other flavor throughout the space. And typically we find that the system shows an irreversible and steady state behavior in time, and typically in the nonlinear regime the length of the polarization vector which captures the amount of flavor content basically shrinks for different velocity mode, and there is an irreversibility in the system even if it starts with a reversible equation of motion, and there is a steady state in time. So to capture the physics of this results in the nonlinear regime, so we typically introduce two concepts. Basically, one is this multiple diffusion. To understand this, we actually write the equation of motion in terms of these multiple moments, which are defined as the different moments of this polarization vector, the Legendre polynomial moments. And this basically reduces the equation of motion to two equations for different multiple moments, which are labeled by this n index. And then we use the concept of coarse graining over the spatial direction, and then for large number of multiple moments we get a basically equation which looks like a diffusion equation in multiple space. And then plus fact that n going to a times n and t going to a squared times t makes the system equation of motion basically same. So basically there is a this basically the solution should have the functional form which is something of like n square by t form. This symmetry transformation reduces this partial differential equation for each multiple moment to a simple ordinary differential equation. And one thing to note that we have in this method, we have actually solved the problem of this huge phase-space dimensionality and non-linearity of the problem, because this huge differential equation, which is actually non-linear and basically also a lot of equation coupled, we have made it a linear equation, which is actually instead of a PD, it's an ODE, and also decouple the system where we can solve for each multiple system. So this reduces the huge phase-space dimensionality and non-linearity of the system to a simple ordinary differential equation, which can be easily solved and the solution looks like this. Typically, the solution represents one important thing, that for large multiple moments, what happens is that the power flows from the low values of multiple to higher multiple moments, and coarse graining of this system introduces an irreversibility in the time, and as a result also shrinking in length for high multiple moments. So basically there is a huge power flow from low to high multiple moments, and due to this coarse graining that we have introduced, there is also an irreversibility in the time even if we have started with a time reversible equation of motion. So this is actually an important result where we introduce why there is an irreversibility in the system even if we start with a reversible equation of motion, and how is the power flow happening between different multiple moments. So, and then we introduce another concept which is known as transverse relaxation. So what happens is that due to this huge flow of power from low multiple moments to high multiple moments, so what happens is that basically once this like here we have shown like how this how the Hamiltonian basically like the parallel and perpendicular component of the Hamiltonian, so how it behaves as a function of time for different lepton asymmetry. So typically what we show is that for different velocity modes, so to give a better pictorial representation, let's see. Okay, so what happens is that we just 1 minute. Sorry. Oh, sorry, just 1 minute. Okay, so okay, so yeah, so typically we show like for different velocity modes, when the transverse so basically what is transverse relaxation here. So basically we can visualize the equation of motion in terms of a spin which is acted upon by a Hamiltonian, which has a parallel and a perpendicular component. So what happens due to this flavor conversion or the diffusion in multiple space, what happens is that the perpendicular component grows of the Hamiltonian grows, and the parallel component decreases. So as a result, the polarization vector actually shifts from its like initially it is aligned along the z component, but due to this due to the due to the increase of this perpendicular component of the Hamiltonian, basically the polarization vector reaches the transverse plane, and when it reaches the transverse plane and the perpendicular component of the Hamiltonian becomes of the same order as the parallel component of the Hamiltonian, the velocity modes gets like due to this transverse relaxation process, the different velocity modes gets depolarized. So basically this happens only when the Hamiltonian of the perpendicular component of the Hamiltonian reaches the becomes the same order of magnitude as the parallel component. Then only this polarization vector shifts to the transverse plane, and due to this transverse relaxation process, it gets depolarized. And to give a pictorial representation of what I mean by this is we can look at this picture. So what happens that the initial or at the initially all the polarization vectors are along this direction, and after when the Hamiltonian becomes the perpendicular component of the Hamiltonian grows, this polarization vector reaches this transverse plane, and then due to this T2 relaxation process basically randomizes between different spatial direction, and as a result the spatially averaged component of this polarization vector basically sinks. As a result, the length of the polarization vector, if you calculate after spatial averaging, which is known as coarse graining, you can see that when it reaches around the spatial in the transverse plane, due to the shrinking of the perpendicular component of the polarization vector due to transverse relaxation process, the length of the polarization vector shrinks because the parallel component has already shrunk. So this is what is known as T2 relaxation process, and it occurs when there is always sorry. And this happens only when the like the perpendicular component of like the parallel component, like polarization vector, reaches the transverse plane. So typically we can see for different velocity modes when typically when the each parallel component of the Hamiltonian and the perpendicular component of the Hamiltonian becomes of the same order of magnitude, we can see that the polarization vector shrinks due to this transverse selection process, and this amount of shrinking actually depends on the lepton asymmetry also of the system. So this process actually is similar to the system in condensed matter also, where there is a spin and there is a perpendicular magnetic field applied to the spin, and then the spin flips, and when it reaches the transverse plane, it basically randomizes, and as a result the total length of the spin shrinks, and we can compare to the spin to here as the polarization vector, and the magnetic field as the basically Hamiltonian. So then this picture becomes very obvious, and this shrinking amount of shrinking depends on the velocity mode as well as the lepton asymmetry of the system. So which is very clear from these pictures, because typically for large lepton asymmetry, all the velocity modes are not getting basically becoming getting relaxed. There's only some of the velocity modes are relaxed, only for which the perpendicular component reaches the same order of magnitude as the parallel component of the Hamiltonian. But for smaller lepton asymmetry, we see almost all the velocity modes satisfies the condition that the perpendicular component becomes the same order of magnitude as the parallel component of the Hamiltonian. As a result, all the velocity modes for all the velocity modes, the polarization vector basically shrinks for lower lepton asymmetry. So this is one result which determines why there is a shrinking of length, or why is there a irreversibility in the system. So to capture the amount of this, so due to this transverse reaction process, one can see the polarization vector parallel component always reaches 0, which indicates there is a favor depolarization in the system, which means that the typically neutrino and electron neutrino and antineutrino electron neutrino and the other flavors become basically of 50% level. So this flavor to capture the amount of the flavor depolarization, so you introduce a method where we keep the where we expand the polarization vector up to linear order and use the lepton number conservation of the system to derive the something known as depolarization factor, which is defined through this quantity. And typically this depolarization factor will represent the amount of flavor depolarization in the system, because if SP final is basically equal to SP initial, then basically FD becomes 0, which indicates there is no flavor depolarization, and the polarization vector is stuck to its initial value. But when this polarization vector becomes 0, then this FD will become 4.5, which represents there is a complete depolarization in the system. So using this multiple expansion of the polarization vector, and also the lepton number conservation, which can be easily found out from the equation of motion, that typically this equation of motion, if we spatially average and use the periodic boundary condition, this gives rise to the fact that the n equals to 0 moment of the system is basically conserved in the spatially average sense, and which is represents the amount of lepton number present in the system. So this conservation along with the multiple expansion, it helps us to introduce these two this formula for the depolarization factor, which will actually capture the amount of flavor depolarization at the in the nonlinear regime, uh, uh, purely analytical point of view, no numerics, is purely analytical. And this analytical formula actually has dependence on the velocity modes and also on the lepton asymmetry of the system, as can be clearly seen from this plot, where one can see that the dotted line represents the our analytical results, and the numerical results is basically the continuous line, which has a good match up to the linear order. uh, and one can see the amount of flavor depolarization actually if we see that the negative velocity modes basically gets totally flavor depolarized, whatever the lepton asymmetry is there present in the system. But the positive velocity modes, the amount of the flavor depolarization depends on the lepton asymmetry of the system. And typically our formula and also the numerics predicts that for larger lepton asymmetry, uh, we will have basically lesser flavor depolarization, but for smaller lepton asymmetry we will have larger flavor depolarization. So yes, yeah. So typically uh, uh, this is something that happens in the nonlinear regime, and we have introduced the first analytical way to determine how much is the content of flavor in the at the late time basically. uh, to conclude in this part, we have presented an analytical theory of fast neutrino flavor conversions in the nonlinear regime. We showed fast flavor conversion can bring neutrino flavors close to each other, which is known as flavor depolarization, and also cause irreversibility in the system. T2 relaxation, which is known as the transverse relaxation and multiple diffusion, basically governs such behavior. And finally, we gave a strategy and a formula for computing the extent of flavor depolarization. So this is the first part of my talk, which represents why there is a how, when, and to what extent the flavor depolarization happens, and why there is an irreversibility in the system. Uh, just 1 minute. Okay. Now I will go to the just next part of my talk. Basically, okay. So to give a hint of what are the phenomenological consequences, like this flavor depolarization can cause a significant increase in neutrino heating rate and change the uh, sorry change the explosion scenario, and this will allow us to also detect the final neutrino signal from a supernova explosion, because this calculation determines the neutrino signal at the nonlinear regime. And this can be an interesting probe for testing the neutrino-neutrino self-interaction, and this final output when implemented in the simulation can give what is the amount of nucleosynthesis, and also various sorts of neutrino astrophysics can be expected from this final neutrino signal, which we can detect from this formula. Okay. To now, in the next part of my talk, I will introduce typically how did we extend our system to multidimensional framework, in 2+2+1 dimensional system. So we did actually a calculation to detect so in the 2+2+1 dimensional system, which is far beyond what people have done in the previous studies. So typically, to explore our system, we have considered 4 scenarios, uh, uh, mainly 3 scenarios, where we have considered the neutrino angular distribution can only have a forward axis, and as a result can have only one single crossing. It can have forward and backward axis, which can introduce many number of two crossings, and also a turbulent profile where it can have multiple crossings due to the fact that neutrino and antineutrino electron distributions are almost very close to each other, which can mimic the basically realistic scenario where there is a turbulence in the profile, and the neutrino and antineutrino distributions basically are very similar to each other and basically crosses at various points in the angular distribution. So typically, to mimic these 3 scenarios, we have taken angular distribution of these 3 kinds, which represents this single crossing, double crossings, and also the turbulent profile. And then used we also developed our general dispersion relation solver to basically capture the linear growth of the system. So basically, our system can be in the linear regime can be represented by a dispersion relation by basically you making this equation of motion, linearizing it. We can get a dispersion relation which captures the linear growth of the system. So this dispersion relation, we have introduced a general method to solve this dispersion relation, where where for the k equals to 0 mode, this dispersion relation gives a simple algebraic equation which can be easily solved, and then we can use this as an initial guess to further propagate our solution very close to this k equals to 0 point, and then use this solution at k equals to 0 point to further propagate at different radius. So this is something known as the iterative method, and we use this f-solve and quad solver to solve that the equation of this dispersion relation at higher radius. This solver uses this method of Powell's conjugate method and adaptive quadrature method, which which can typically solve this nonlinear transcendental dispersion relation very easily.
So for a reminder, you have 5 minutes left.
5 minutes. Okay, fine. Okay, thank you. So I just let me just quickly go to our main results of this multidimensional framework. So for the forward axis or the single crossing, we find that linear growth rate has the same symmetry as the neutrino angular distribution. Basically, neutrino angular basically we also find that k equals to 0 mode for this this type of forward axis scenario is basically unstable and gives rise to a linear growth. This growth rate also decreases as a function of as the k increases, and this decrease is much slower along the axis where there is a symmetry for the angular distribution. And we also find that the Fourier mode with the maximum growth rate is located along the axis of the dispersion relation, which is non-symmetric, about which there is no symmetry of the dispersion relation. And we also find that this depends on the lepton asymmetry of the system, where if we increase the lepton asymmetry, basically the overall linear growth rate gets suppressed. For double crossing or for both forward and backward axis scenario, basically typically most of the results are same, but only k equals to 0 mode is stable in this case, and the radial distribution has a Lorentzian shape as a function of k. So and also the lepton asymmetry, as we increase the lepton asymmetry, the overall growth rate of the linear regime basically shifts. One important result I will just move to is that of the turbulent or multiple crossing scenario. Here we have an interesting result which says that the linear growth of such dense neutrino system has a dependence on the number of crossings in the angular distributions, and typically, if we show analytically using saddle point approximation from the dispersion relation, that typically the dispersion relation using saddle point approximation can be reduced to the and can be solved to say that this linear growth rate of the system has a dependence on the multiple crossing, has a dependence on the number of crossings of the system, and typically it varies as 1 over m, where m is basically the number of crossings, where which says that if the angular distribution of neutrino has large number of crossings, basically the linear growth of such systems will be highly suppressed. And this we find a good agreement with our analytical result, that typically when we solve this system using our dispersion relation solver and fit with the 1 by m formula, we see a good prediction of our formula. And typically this is an important result which says that ELNs with large number of zero crossing can lead to a relatively smaller growth rate. And this can be an important result because for many realistic scenarios, because typically in realistic scenario there is a turbulence in the system, and typically electron neutrino and anti-electron neutrino can flavor angular distributions can be very close to each other, and there can be lots of crossings in the system. And due to this suppression, there can be a huge the flavor conversion in the linear regime can be highly suppressed, and this can have important signatures in the neutrino astrophysics. So basically, I guess I am done. Hello.
Okay, thanks, Xiaoming.
Hi.
Yeah, okay, so let me see. So Emo has a question about the physical source. Emo, would you like to go ahead?
Just 1 minute.
Sure. Can you go to the one of the beginning slides?
Okay, yeah, sure.
So I can try to find where.
Yeah. Okay. Which one are you talking about?
Go one forward.
This one?
One forward. At the beginning of, yeah, okay. So can you, yeah, okay. Can you go one more forward where you were defining the two flavor initial conditions?
Oh, I see. Just 1 minute. I guess I guess this one. Initial condition.
So what is the physical source that gives you this 10 to negative 6 delta function for the transverse? Like physically, what does it mean to have?
Okay, yeah. So basically, we don't know what is actually the initial condition when the neutrinos are emitted. We don't know actually the typically like if we assume that the neutrinos are almost like in the realistic case, basically when the neutrino density is very high and the in the supernova, basically the neutrinos are almost in the electron flavor. We can basically this can be understood from the like basically neutrinos are almost in the heavy mass eigenspace, which says that the neutrinos are emitted almost as the electron flavor. But typically this this perturbation, initial perturbation doesn't have any physical understanding, but the the reason we have chosen this delta function is basically this delta function means like we are giving a specific seed to only a space only z equals to 0 point, which will give perturbation to all the k modes in the Fourier space. So this is the reason of choosing such delta function, which will give the perturbation to all the k modes. So we don't want to give any preference to any sort of k modes, because we don't know which k modes initially get excited from any physical source. So that's why we wanted to give a initial condition which will give the same preference to all the k modes. So in the Fourier space. So that is the reason for the choice of the delta function in space in space basically. But truly speaking, there is no realistic understanding why what is the initial perturbation for in the realistic case. There is no realistic understanding. So we wanted to give this because we wanted to give all the k modes the same footing basically. Yeah.
Right. Thank you.
Yeah.
Okay, George has a question.
Yeah.
George?
Yeah, can you hear me?
Yeah, I can hear you.
Yeah, very good. Thank you for this talk. It was very interesting. So kind of this is a little bit building on Ermal's question. So, if I think about what's important in a real environment, like a supernova or a binary neutron star merger outflow, it's really where flavor conversion sets in radius and time. And if I look at that, if I look at your very simplistic model here, then that of course is determined mostly by the difference in angular distribution between different flavors, and also the energy spectra and the lepton number to some extent. So I worry a little bit that this diffusion of power in flavor transformation to smaller scales, which by the way we have seen. I mean, Luke Johns and Hiroki Nagakura have seen this as well in angular moment calculations. But all of that takes place fairly quickly. But the thing that's most important for supernovae, for all those things you mentioned that we've been looking at for a very long time, nucleosynthesis, composition, electron fraction, heating, et cetera, that really, the important thing there is where this sets in. And I worry a little bit that once you start changing the flavor transformation, you also change scattering, and therefore you change the angular distributions of different flavors, because they typically might have different energies or fluxes, for example. So that's one issue. And then the other issue is that we don't really even know what those are, right? Even conventional Boltzmann transport calculations are not going to be able to give you a very good, or at least very convincing story for what the outflow, what the emergent neutrino energy spectra are. It's going to be equation of state dependent. Ultimately, it's going to depend on scattering also, and the way you treat scattering. So I just wonder your thoughts about those issues.
Yeah. So we have neglected. So you mean so we, in our calculation, we have actually neglected the scattering. I mean the collision term. Yeah, that is basically making the system.
Yeah, and that's kind of what I'm pointing out, is I'm a little worried about, and hangs me up in my thinking about this whole problem, is that if we're really interested in angular distributions, then you have to worry a little bit about how scattering is really resetting those, and maybe you can make arguments about the length scale of the fast flavor conversion phenomenon versus typical mean free paths for transport mean free paths for actual direction changing scattering. But I'm still a little bit worried, because if you look at in your calculations, if I got your talk right, it was the backward moving neutrinos that really had a lot of leverage in whether you got depolarization or not.
Right. Yes. Yeah. Right. Yes. So basically, this is actually a simplistic calculation. Correct. That I agree. But one thing is that the angular distribution that we have chosen to be a box spectra, this is something I would say approximately matches the realistic profile up to 0th order level, basically. But yes, we have neglected the collision. That is one thing one has to check, like how can things change the collisional term that you are mentioning. But, yeah.
Okay, thank you.
Yeah.
Okay, Sherwood has a question about the Lorentz shape. Sherwood.
Yeah, so first of all, thank you very much. This is very neat work, and it's a lot of fun to hear about it. So I actually have lots of questions, but I'll stick to one for now. You mentioned that the dispersion relation has this Lorentzian shape.
Yes.
Is that something that's general for all distributions? Is it clear where that comes from, and is it really formally Lorentzian?
Lorentzian in the sense, so first of all, this is in the linear regime, by the way, this calculation that we are doing.
Mm-hmm.
So Lorentzian in the sense, it has a distribution for which the smaller, so K modes have a initial growth which is quite suppressed, and then after some higher K modes, it becomes again large, and then again at high K modes, which basically means the smaller wavelength modes, basically the linear growth is again suppressed. So this is typically the nature we find. Basically, this we called as a Lorentzian nature. So I mean, the typically so this is something we get by analytically solving the dispersion relation. So
right, but I mean, so is it formally Lorentzian, or is it just like a bump?
No, it's actually like a bump, like we just compare, say, yeah, exactly.
Okay,
but,
and does it look like that for all initial distributions that you might try? Do you expect to see like a no matter what, it should look like that? It'll just move around like where it is or how high it is, but it always look like a bump like that?
So typically this nature we find only for system which has this double crossing scenario, which means that there is a forward and also a backward excess of neutrinos at the initially. This type of double crossing scenario, which I actually just 1 minute, which actually I mentioned as this type of scenario where there is a crossing in both in the forward and backward axis. And typically this type of ELNs, like neutrino angular distribution, has this nature that in the linear regime they has this linear this Lorentzian shape for as a function of k. So this is a general feature which appears for systems which has this both forward and backward axis, but this doesn't appear for systems which has only forward axis or the different only single crossing type of scenario where there is only forward axis. It doesn't appear, this shape doesn't appear for such systems, but this is only true for this type of ELNs where there is a forward and both backward axis. And this is true for initial conditions, in the sense like we have only used initial conditions which is typically starting neutrinos with electron flavor, but that initial condition we didn't vary, but we varied different types of ELNs of this type, and we see this feature to be a generic feature. Yeah.
Okay, thanks.
Okay, Shashank has a question about the box spectrum. Shashank.
Yeah, so I did not understand why you were saying that box spectrum is realistic to first order.
Oh, I mean, what I mean by that is that typically in the just 1 minute. Typically in the realistic profile of a supernova, there is it can be approximated it doesn't have too much crossings. Like it is like up to if we just Taylor expand up in the angular modes, you can just approximate the realistic profile up to fewer angular modes. So which means that typically in the in the zeroth order limit, we can think that there is only a single crossing. So box spectra kind of matches that scenario where there is up to zero, like typically as the realistic supernova profile can be approximated up to fewer moments. One can say that up to the zeroth order limit to have at least is crossing in the angular distribution, one can choose a box spectra, which is quite good approximation to the realistic profile.
Okay.
I think Prakash has a question about wooden collisions destroy coherence.
Oh, I see. Yes, collisions can destroy coherence, but typically in our calculation, as Fuller mentioned, actually, George mentioned, actually, we didn't include the collision term and check how collision affects all these whatever results that we have developed. But typically in some of the papers where they have made some calculations like introducing collisions, there I guess they find that there is a loss of coherence in the system. But in our result, the loss of coherence is totally not due to collisions. It's just due to the basically the coarse graining of the system, and also basically this transverse relaxation and multiple diffusion basically introduces and irreversibility and a time direction in the system, which introduces a decoherence type of feature. But there is no collisions in our calculation. But this is only happening due to this coarse graining and multiple diffusion and transverse relaxation process, which introduces this decoherence behavior. But we don't know what will happen if we include collisions. That one has to check.
Okay, Ian has a question.
Yeah, hi, Soumya. Thank you very much for the talk.
Oh, hi.
So
Yeah, hi.
I was wondering, so you showed this box that is basically centimeter scale. Is this correct? Right. So it's like really there's a box that that you showed that is essentially centimeter scale. It's like really small length scales somewhere. So my point is, how do you make the connection? Yeah, that one. Right. So that's yeah, even smaller, that 1 centimeter. So I was wondering, how do you make the connection to a more realistic, say, supernova environment, which is typically, you know, a couple of at least kilometers? Because I don't see how can you extrapolate from what happens in the microphysics to the macrophysics. So I was wondering whether you can get away with a coarse graining and saying, okay, you might not be able to resolve the centimeter scales, but you can say something about what happens in the kilometer scale. What is your take on this? Thank you.
Okay. So I mean, I see. So your point is like I guess this calculation typically doesn't depend on the box size that we choose. Actually, basically, I mean.
Okay, so if it doesn't depend on size, then what happens if you take a kilometer times kilometer box? Do you see the same?
Yeah, that's what I see. So saying that all this physics doesn't depend on the box size, though, and doesn't depend. So the final state is insensitive to whatever initial condition we choose. My initial condition in the sense, like typically when we give we have introduced a initial condition where we have given a seed at a specific point of the box, right? Delta function seed. So we find that the final state is independent of whatever the choice of like wherever we put the seed and whatever we type of initial condition we choose for the box. And also typically is independent of the box size, I guess. We also check that if we increase the box size and decrease the box size, it doesn't change the final state, like final state in the sense the ultimate answer that we get, which is this flavor depolarization picture, it doesn't change. Basically the answer remains the same. Independent of initial condition, like independent of what type of seed we choose for the box, we wherever we choose the delta function, wherever the point we give the initial seed, even if it's a delta function or even if it's an extended seed, it remains same, and also independent of the box size. True. But it depends on the ELN basically. Yeah. I mean, is it answering your question? I mean,
Yeah, thank you.
Okay.
I think Prakash have one more question about hazard calculation with only collisions being performed.
Sorry, can you repeat the question?
Yeah, is there a calculation with only collisions being performed?
Oh, has a calculation with only collisions have been performed? Okay. No, but only in one. Okay, so I just 1 minute. Like typically people have performed calculations with collisions, but they didn't go to highly nonlinear region probably to see what happens that we typically see. Like one has to include calculation with collisions and go to highly nonlinear regime to see our results are true or not. So I don't think people have performed this type of nonlinear calculations at highly nonlinear regime and at high late time basically, with including collisions basically. So basically, that's what I guess. Yeah, so that is my answer. Like typically people have not considered collisions to very highly nonlinearism, if I check, and also typically with a very general system.
Yeah. Okay.
There is one here.
Yeah, Prakash, does this answer your question? Maybe you would like to ask by yourself for the follow-up question.
Yeah, that sort of disturbs me. I mean, people are sending me all sorts of archive articles to look at. There is no chance I'm going to look at it now. In my experience, at least in heavy ion collisions, of which I'm fairly familiar with, collisions were very important, as well as the Vlasov terms that the speaker was talking about. The two play a intermingled role. Now, even with collisions alone, as the speaker mentioned, Soumya, it is a highly nonlinear system because a Boltzmann type equation is nonlinear by definition. It's an integral differential equation. So I'm wondering whether doing only one captures all the features of reality, so insofar as we think it would be. So please don't send me more archives. It doesn't help me. I just want to know what transpired in those collisional calculations to whatever accuracy they were done. Anybody can answer.
So can I jump in and answer the question?
Please.
Yeah.
Okay. So I did a calculation actually quite recently where I did the calculation with collisions in the nonlinear region, but it was assuming a homogeneous system. And there we found that under certain circumstances, it is actually possible to get an enhancement in flavor convergence for the right angular distributions. For some angular distributions, there's a suppression. For some angular distributions, there can be enhancement of flavor convergence.
Yeah, but that is choosing, things, right?
Yes. So it was not a self-consistent calculation in that sense. You're right. And we don't know how to do it self-consistently because, as you mentioned, it's like a really complicated system.
Yeah.
Okay, thanks.
Okay.
I think that's a very important question that someone put up there. Timescales for collisions and oscillations.
Yeah.
Sherwood is always a troublemaker. The kind I like.
Hello, Soumya.
Yes.
Okay.
Yeah, is there any one question? Yeah.
Yeah, I think Shaw would want to know just like what's the relative time scales of the collisions and oscillations.
Yeah, it's a little bit of a leading question.
Okay.
He knows the answer.
That's it. Okay. Yeah. So what is the question actually? Hello.
I just wanted to, with respect to the ongoing discussion, just to bring up the disparity between the collision and oscillation timescales. I think makes what I want to say is work like yours is relevant for all of the complicated stuff that happens before collisions can really get at modifying the distribution. So I think Soumya's calculations have a lot of ability for those first few microseconds. That's on a shorter time scale than collisions can eventually very dramatically change the overall result. But
okay. Yeah, I mean, yes. Probably one needs to include collisions to check what differences happens, but we didn't do that. Yeah, so maybe one has to maybe collision can't change things a lot. one has to check. I can't say what will collision typically change the thing, how much change will happen due to the collisions.
It also depends on length, not just the time scales, the length scales.
Yeah, exactly.
Yeah, so I think my point is I think Soumya's calculations are very relevant until that happens.
Yeah.
Do the simplest things, guys. I mean, you guys are all doing highly complicated stuff. Or just because you are young, you have the ability to do it, you have to do it?
Okay, so I think, yeah, so let's thank Soumya again, and we will see you after 2 weeks. Thank you, Soumya, for the nice talk today.
Yeah.
Thank you, that was a lot of fun.